In this video, we'll discuss Blackbox hyperparameter optimization. This is the simplest formulation of the hyperparameter optimization problem, but also the most widely applicable. Let's dive right in. Blackbox optimization methods for HPO. As the name says, in Blackbox hyperparameter optimization, the interface of the optimizer is that of a black box. So we have a hyperparameter setting, theta, that goes into a black box, and out comes an f of theta, which is the validation error achieved with this hyperparameter setting. Having this interface of a black box simply means that the only mode of interaction with this function f is to query the function value at a given hyperparameter setting theta. And there is no other mode of interaction with the black box. The black box optimization problem is simply to find the theta star that minimizes this f of theta. And for the hyperparameter optimization problem, we then define this f of theta as this loss function that we've seen in the definition of hyperparameter optimization before. Now, it's important to note that in black box optimization, this function may not actually be available in closed form, it may not be differentiable, it may be noisy, and in fact, that is exactly the case for our f of theta here, because, well, this loss function that is actually defined by running an algorithm, it often has discrete parameters, there's often noise, this algorithm depends on a given seed, and so on. So these are exactly the settings that we do have in hyperparameter optimization. The first hyperparameter optimization method that I would like to talk about is the simplest one, random search. Random search selects configurations uniformly at random in a completely uninformed manner. It is a global search algorithm, so at least it doesn't get stuck in a local region. It also parallelizes nicely, and it's at least better than grid search, and grid search is another very widespread approach. And that is shown down here. So here we have a grid search layout, and here we have a random search layout, each of them with 9 function evaluations. So these dots here are the function evaluations. And what's plotted here is a case where there are 2 parameters or hyperparameters, one that is important and one that is unimportant, in the sense that it doesn't actually affect the validation accuracy much how this particular hyperparameter is set. And for this parameter here, or hyperparameter, important in the sense that, well, there is a clear peak here that if we optimize this hyperparameter well, then validation accuracy is much larger. Now, one problem that grid search has, in contrast to random search, is that it doesn't use this budget of 9 function evaluations very well. In fact, for each of the hyperparameters, it only looks at 3 different values. And those values are then duplicated a lot of times, in this case 3 times. And this actually makes it miss this peak here. So just with these 3 different parameter or hyperparameter values, we don't see this peak. In contrast, for random search, we have 9 different values for this hyperparameter, and we do actually see this peak. We also have 9 different values for this hyperparameter here, so we didn't know ahead of time that this parameter or hyperparameter here is going to be unimportant, and this parameter here is going to be important. So the same would have actually also worked if this here was important, then we would still figure that out. So I also said that random search parallelizes more nicely than grid search. And while grid search is actually already quite convenient in terms of parallelization, because you know ahead of time which hyperparameter settings you want to evaluate, namely this grid of 9. And you can then simply use 9 compute nodes and evaluate one of these hyperparameter settings on each of them. However, if actually one of these jobs crashes, say this one, then the resulting design of the other 8 hyperparameter settings is actually not a valid grid search anymore. Whereas in random search, say if this one node here died, the other 8 random points still define a valid random search with 8 points. So that is quite nice. All right, so this was random search. It's completely uninformed, but it's a global search that at least doesn't get stuck in a locally optimal region. The opposite, in many senses, is a local search. This is also sometimes jokingly called a graduate student descent because it's what many graduate students actually implicitly do. So you start with some hyperparameter configuration because you have to actually initialize with something in order to run your deep learning algorithm. And then typically, as humans do, you only modify a single hyperparameter. And then if results on a benchmark set improve, then you keep the new configuration. And you keep on doing that until, well, until there's no improvement possible anymore, or until it's good enough, or time is up and you have to submit your paper, or your course is done, or your exercise is done, and you simply have to stop. So this is something that we all have done at some point. I definitely have done this many times. And it's instructive to realize that this is nothing but a manually executed first improvement local search. In contrast to random search, this is perfectly greedy and it can get stuck in local minima. But it can also, in some cases, be a lot better than random search. If you, for example, think of a function that depends on a single hyperparameter, and that goes like this, then local search will quickly realize that you need to go here and keep sampling on this point over here, whereas random search will happily just evaluate anywhere without taking into account that on the right side, you're getting better values. All right. The third method I want to talk about is a bit more sophisticated. This is called Bayesian optimization. And the way this works is to fit a probabilistic model to the collected function samples theta, f of theta. So we have evaluated our function at different points, theta, and we got the function values f of theta. And we fit a model to that that predicts for new points, theta, what the performance will be. And we use that model in order to guide our optimization to trade off exploration versus exploitation. So if we visualize this, here at t equals 2, we have already evaluated our function at 2 points. So we have theta here, and well, this dashed line here is the true f of theta. So we have seen that at these 2 points, and let's say we don't have any noise. So we have perfect knowledge at these 2 points, but away from these points, we don't have perfect knowledge, and we have uncertainty in our model. So this is often expressed by a so-called Gaussian process that is fit to the model. And here we have the mean of that Gaussian process, and we have the uncertainty band. So this is 1 standard deviation of our predictive uncertainty. And so this uncertainty grows away from our data points. And at the data points, we have 0 uncertainty. So we then use this probabilistic model in order to trade off exploration and exploitation. We want to explore in areas where we're uncertain, but we want to exploit that we know something about the function. In particular, we know where it's predicted to be high. And in this case here, we're maximizing. So a good point that would trade off both having a relatively high prediction and a relatively high uncertainty would be this point. So we can quantify this utility, this likelihood of helping us in the search by the so-called acquisition function that is plotted down here. So this is some function that is defined purely in terms of the predictions of our model, of our Gaussian process in this case, and we can simply maximize this function in order to then pick this point here and then evaluate at the point that maximizes this acquisition function And there we then actually see that the true value lies down here and not up here as we expected, and also not up here as we hoped. And based on this, we can then refit our model and recompute our acquisition function down here. We maximize the acquisition function again and next evaluate at this point here that actually optimize this acquisition function here. And we can iterate this process as long as we have time. So this is an approach that is actually very popular in the statistics literature, and it's actually already more than 40 years old. It's very efficient in the number of function evaluations because it uses all this information and does all this reasoning about where to evaluate next by optimizing the acquisition function in between evaluating the function. So notice that over here on the right in this example, we've only in total evaluated 4 function values, and we've done all this work here just to get this one new point and all this work here just to get that point. And so we're doing a lot of thinking before we evaluate next. So if your function evaluations are cheap, for example, on the order of seconds, then Bayesian optimization is probably not worth it. But if your evaluations are more on the order of hours or days, then Bayesian optimization is definitely getting more worth it. And that's why for deep learning, it's actually sometimes a very good idea. Bayesian optimization also works when the objective is not convex and noisy and has unknown derivatives, etc. So these are all properties that we have in hyperparameter optimization, and that's why Bayesian optimization is actually a very good match. And there's also recent convergence results that if you make some assumptions on the function, such as smoothness, or that the function is an element of a so-called reproducing kernel Hilbert space, then you can actually get some convergence results based on the acquisition function that you choose. Okay, so this is Bayesian optimization in a nutshell. And the thing that you should really take away is that here you have this probabilistic model, and you use this probabilistic model in order to trade off exploration versus exploitation. And one thing that this probabilistic model needs is a way to quantify our uncertainty. All right, so one variant of Bayesian optimization that doesn't actually look very much like Bayesian optimization at first glance is this method called TPE, the tree of Parzen estimators. While standard Bayesian optimization uses Gaussian processes to model this P of f of theta given theta, what TPE does, rather, is to fit a generative model that predicts a probability that a hyperparameter setting theta is good. Is good, what does that mean? Well, it means it's better than other hyperparameters. It's a generative model that gives you hyperparameters that perform well, and it does so by using a non-parametric kernel density estimator in order to fit these good points. And in this case, these are the good points here. We're minimizing, and there's a single hyperparameter here, and well, those 2 points we have evaluated, and those are bad. So we're fitting kernel density estimators to the good points and to the bad points. And then what we do next is we compute an acquisition function that is actually the probability of being good divided by the probability of being bad. And that gives us this acquisition function here, and we will evaluate on the right. Now this new point here actually also was a bad point, so we update our kernel density estimator for the bad points and then get a new acquisition function that is again the probability of being good divided by the probability of being bad. And now we'll again optimize this acquisition function, and now we get this point here. Notice that now we're saying this point here is bad, whereas previously we said it's good, and that is because, well, it's not anymore one of the best points. And so only these 2 points are now the best points. whereas the other 4 are now counted as bad points. And so then we refit again the kernel density estimator for the bad points, the kernel density estimator for the good points, and iterate this whole procedure. So this technique is very efficient because all that we're fitting is kernel density estimators, whereas Gaussian processes are actually cubic in the number of data points. This here is only linear in the number of data points. And another nice thing is that we can also incorporate priors. So whereas in standard Bayesian optimization, the priors that we have as humans don't really fit with the priors that Bayesian optimization wants, here they directly fit. So what do I mean by that? Well, in Bayesian optimization, we have a prior on what's the probability of f of theta given theta. So what's the probability of getting a certain validation accuracy given a certain hyperparameter setting? And often that's not quite what we have in mind for our algorithms, but what we do have in mind is what's typically a good hyperparameter setting for something like the learning rate. That is something that we know from previous expertise and experience, but we don't know for a new data set which validation accuracy we can expect with different settings of the learning rate. So here we can simply have a probability of the hyperparameter setting being good, and we multiply it into our kernel density estimate. And well, we can do that here, and we can't do that with standard Gaussian processes. Unfortunately, one of the disadvantages of this tree of Parzen estimators is that it is not quite as sample efficient as Gaussian processes. So that's one of the negative points of TPE. The next method for black box hyperparameter optimization I would like to talk about are population-based methods. And population-based methods, as the name says, keep a population of different hyperparameter configurations. And they do so in order to maintain diversity and also improve over time fitness of this population. Now, one popular instantiation of population-based methods are so-called evolutionary strategies. Evolutionary strategies have a mean of the population and then sample individuals around that mean. So this is one hyperparameter and this is another hyperparameter. So this is of course in d dimensions for d different hyperparameter settings. Then all of these are being evaluated, and these green hyperparameter settings here are the best. And then what the mean does is to move over to the mean of the best ones of this current population. And then this method iterates. The popular variant of CMAES, the covariance matrix adaptation evolutionary strategy, also on top of that keeps a covariance function that it adapts. So initially here in this example, there's this relatively round covariance matrix. And then after the method sees that points over here are quite good, it elongates this covariance along this direction, goes a bit more in this direction, and then homes into the really good region. And this CMAS algorithm is actually very competitive for black box optimization if you have cheap black box functions. So if you have a function evaluation budget in the hundreds, thousands, or millions, this is actually the state-of-the-art algorithm. And for more expensive black box optimization problems, it is still quite competitive. In particular, if you have parallel resources, then it can actually handle these parallel resources really well and achieve quite good performance for hyperparameter optimization of deep neural networks. One limitation, however, is that it is limited to purely continuous hyperparameter settings. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video and think about them to activate the material. Thank you, and I'll see you in the next video.